Yeah, for the sake of those who are absent, this is what I've been telling you. The two conditions for static equilibrium. I just wrote it down. I thought you must see it. Just reviewing it before we do those problems. What are the two conditions? Condition number one, net force must be zero. That means net force along the x-axis, along the y, or the z. Whatever axis you take, the net force must be what? Zero. There should be no... I know we were talking only about the y-axis, isn't it? And all these problems, up and down, but it's true for anything. Second condition, what is that? Net torque must be zero. That means the sum of the torques about any axis, but if it's clockwise, it should be exactly equal to the counterclockwise. So when you add them up, you get zero. Okay, those are the two conditions, and this is your problem number one, the figure. One meter. What else is given? 3 meter. Okay. Yeah, we stop. Okay, a little bit more. The reaction on that support, FA and FB. Does that make more sense now? Okay. So the question is...
Yeah, where did the 1 meter come from?
I'm giving it to you. I'm giving it to you. I know that without the figure you can't do it. The figure accompanies the question. But it's only that I wanted to give it to you like this. 1 meter and 3 meter. FA plus FB is equal to 93. I did the B part. Okay, I did the B part. I did not do the A part. Do you see why I got the 93? Okay, because the A part is easy for you. I did the B part. So in place of this, what you would get is FA plus FB is equal to, what's your number? 568.4. Very good. Continue. What's the second condition? You take the moments about any point. Let's take the moments about A. Okay, so first tell me which are the clockwise moments. There's only, okay. Wait. Watch carefully. With A as your point of reference, keep your eyes at this point and then say, this force is trying to turn it clockwise. Correct. Okay. And then again with that point in your eye, you look at FB and say that is trying to turn it. What way is FB trying to turn it? Counterclockwise, right? Good, you got it? And what is FA trying to do? What's the torque of FA about that point? Zero, because there's no distance. Because you're taking the force, and what's the distance from that force? Zero. So if you multiply FA with zero, what do you get? Zero. It became easy. So that means there's one clockwise moment, which would be how much? Tell me. You have your number. What was that number? 568.4 multiplied by somebody? 4. 568.4 times 4 is equal to? It's equal to?
2,220.
No. That's the product. But what's on the other side? FB times? FB. How far is FB from that point?
1.
So, is it FB times 1? All right. What is the number? 568.4 multiplied by 4 is equal to FB times 1. I hope you understood. Because 568.4 is the force creating the clockwise, isn't it? Mm-hmm. So you multiply that force with the distance from the end, because we're taking that as the axis. So 568.4 multiplied by 4 is equal to FB multiplied by 1. And again, I'm telling you, this will work wherever you take the axis. So if somebody wants to take the axis right where the person is, it'll still work. But you know why I did not do that? Then you'll have two unknowns. See, why did I take the axis at A? What happened to the moment due to FA? Got cancelled out, right? Because you got a 0? That's why I did that. All right. Solve that and find it. There are two equations. Solve it. So in the B part, FA plus FB is this. And I'm taking moments about A. What happened? It stopped? Okay. The weight of that person. All right, the mass is 75 kilograms. The child. And the question says both are seated at the ends. Did you notice that? So I drew it like that, 75, 25. The total length is 9 meters. And the question says, where should the pivot be placed so that the board is balanced, ignoring the board's mass? First you have to ignore the mass, and then you have to consider the mass. I did it for one case. Hold on. Does that make sense? I did not even make it into newtons this time. I just kept in kilograms to make it easy. And that's how you will proceed from now on, okay? Don't change it in newtons. Just keep it. Are these correct? The force at the fulcrum should be 25 plus, although we're saying force, I know it's in kilograms, okay? Let's keep it easy that way. So the force at the fulcrum should be 25 plus 75, 100 kilograms. Everybody fine? Okay, now take the moments. Take the moment about which point would you like to take it this time? Which is the unknown thing here, right now? Do you know the force F at the pivot? We do. So you could take it anywhere you like. And there's only one unknown, which is X, and you would get it. So I challenge you to take it wherever you like. Some people take it at one end. The others take it at the fulcrum. The others take it at the other end. You know what I'm talking about? And everybody will get the same answer. Try. Unless you are copycats who want to copy me. At that point, it's 75 times 9 minus x. That's clear, isn't it? 75 times 9 minus x is equal to 25 times x. Problem done. So you multiply 75 times 9, you get 675, negative 75x. Take that to the other side, so you get 25x plus 75x is 100x is 675. Then divide by 100 and you would get 6.75 meter. From the child, of course. When you give the answer, you have to give that, depending on how you took x. You could have taken it from the person. You would have got 9 minus 6.75. On number 3, you should have come up with a figure which is almost like this. That's 50 kilograms. 50 kilograms. And 35. And I said, okay, let that child C be there. 25 kilograms. Is that figure right? Oh, question, how do you know that child has to be on that side? That's common sense. Because this child is already heavy. If you put that... Okay. So now, I'll let you work it out. Come on. All right, so that's x. You're taking the torque there at the pivot. Moments means taking the torque, finding the torque. Okay. 35 times 1.8 plus 25x is equal to 50 times 1.8. Isn't that what we said? And so 63 plus 25x is equal to 90. So 25x is 90, take away 63. It's 27, isn't it? So 25x is 27, x is 27 divided by 25. should be 1.08 meter. So number 4, that's where the big sheet is. The horizontal end, the problem says that makes an angle of 3.5 degrees with the horizontal. And I call the tension on both sides Ft. Wait a minute. How do I know that the tension is equal on both sides? Yes, because the sheet is hanging down the middle, isn't it? Because it says the clothesline on either side makes an angle 3.5, so it should be at the middle. All right. Now, have you seen this before? Yes. Ft, yes, Ft is resolved into two components. The horizontal is going to be Ft cos 3.5, and the vertical is going to be Ft sine 3.5. Ft sine 3.5. You do the same on this side. Wouldn't you get Ft cos 3.5 on this side too? Yes. I've not drawn it, but I hope you can understand. Did you? Do you understand that you will get this component to be Ft cos 3.5? So what happens between these two? They cancel out? The horizontal cancel out? So what's the total vertical component now? Somebody? 2Ft sine 3.5. So that means 2Ft sine 3.5 should be equal to mg. Yes. There you go. So the total vertical is 2Ft sine 3.5 and I had to find out the value of sine 3.5 and all that and plug it in, which I did. Okay, remember I multiplied it with 9.8 now because you need to find the tension, which must be in newtons, so that's why. And then I found out that sine 3.5 is 0.061, is it? Is that what you get? 0.061, 5.88, so divide that by this and you have your answer. Ft is 5.88 divided by 0.06. Oh, yeah, 2 times 0.061. That's how I got the 0.122. That is your answer. You know what is amazing here? What's the weight of that sheet? What is the weight of that sheet? No, the weight is only how much? Which means, hold on, just watch. If you were holding that sheet up, you would only have to apply a force of how much? To hold it there. But now, what's the tension in the string? 0.16. Can you explain that? Actually, that's the second part of that question. Isn't there a second part that says, why is the tension so much greater than the weight of the sheet? Because if you're just to hold the sheet straight up, you will only need 5.88 newtons. But now you see that the string has a tension of much more than that. Why? No. Because you're trying to keep something vertically by applying a force that's almost horizontal. Hey, are you getting it?
Like you described torque on the door.
Exactly. No, I think I will